Hey physics students, this is Kaisa Young. For those of you who don't know me, nice to meet you virtually. This is a video with a quick explanation of experiment 6 on the Wheatstone Bridge. I'll give you a little bit of physics background and then walk you through what you're going to be doing for this online lab. So you can follow along in your lab manual here. I suggest that you read it and then watch the video, and then I'll give you a sense of what you're gonna be doing. So let's just get started here with a few thoughts on the Wheatstone Bridge. So the Wheatstone Bridge is a circuit, and I'm going to draw it a little bit differently than in your lab manual so that it matches up with what you're going to be doing in the virtual lab. Often you will see it in sort of the diamond shape like in your lab manual, but when you're going to build it with a PhET simulation, it's going to look a little bit different. You will have your power supply, your battery here, and then we're just going to square off the corners. It is a circuit that consists of 4 resistors. And the purpose of the Wheatstone Bridge, you can tell I'm not the best artist here, the purpose of the Wheatstone Bridge is to figure out the resistance of one of those resistors. So we're going to label these resistors Rx. That's going to be our unknown. That's going to be the one that we are trying to figure out. And then we have 3 others, R, Ra, and Rb. Okay. The reason that it's called a Wheatstone Bridge is because you have these resistors. You can see they're in series and they're in parallel, but they are connected by a bridge down the middle. We are going to put in the middle of that bridge something that we can use to measure the current. In lab, we would have used a galvanometer. In the PhET simulation, we're going to use their little current ammeter thing. So I'm going to draw it as an ammeter. What we're going to do is set the current going. In the simulation, the current will go this way to the right, which is, again, opposite of what I normally do in class, but I think y'all can follow it. So that current is going to come around, and at these junction points, we have junction points at 4 different places on the Wheatstone Bridge. At the junction points, the current is, of course, going to split. So you'll have current going in 2 different directions. Now, you might wonder what happens at the bridge. The way that I've drawn it, and the way that you'll see it in the simulation, is that current will come down this way. So, I said the purpose of this bridge was to figure out what is this unknown resistor. Well, it turns out that that's not too hard of a job if we know all the other resistors and if the bridge is balanced. If we have a balanced bridge, we can use simple rules, junction rules, Kirchhoff's laws, that tell us what's happening with the current and what's happening with the voltage. I'll leave you to read that in the lab manual, as well as Ohm's law, V equals IR, to figure out what these resistances are. So what do I mean by balanced? By balanced, I mean there is no current running in the bridge. So the current, and your lab manual, this is equation 6, Ig, the current through the galvanometer, or in our case the ammeter, is equal to 0. So that is this current right here. Ig is equal to 0. That's a balanced bridge. When you have that, that simplifies all of Kirchhoff's laws and Ohm's law, and you can go through that derivation in the lab manual. And it allows us to very simply look at essentially the ratios of the resistors and see that in this special case, when the bridge is balanced, our unknown resistor Rx is just a function of the other resistors, R times the ratio of Rb over Ra. It is independent of current. We don't need to know what our current is. So what you're going to do today is build a balanced bridge virtually with the PhET simulation. So briefly, let me show you that here. On Moodle, you should find this additional document that goes through the instructions of what you're going to need to do. This lab will have two parts. First will be the PhET simulation using the virtual lab, and then the second part will be some analysis using real data. So the PhET simulation, you will go to Google, PhET physics, you'll click on electricity, magnets, and circuits, and then you will want to look for this one right here, Circuit Construction Kit DC Virtual Lab. The one that says Virtual Lab is the one that you want. When you open that up, you can play that in your browser or download it. It looks like this. Follow the instructions on that document that you'll find on Moodle. You'll need to change a couple of the check boxes. You'll want to see what the values of the resistors are. Change it to conventional. That'll show you how the current flows with those little red arrows. You'll also want to change it here to the symbol form so it looks like the circuit diagrams I've been drawing. Then you start dragging and dropping. Here's your menu over here. Get yourself a battery. You're going to need some resistors. You're going to need some wires to connect it. It's pretty easy to use. It just kind of matches it up as you go. You'll want to build it to look like that circuit that I just drew, which is also here in this document. There's a picture here of what it'll look like, and then there's a picture here of that circuit diagram. So you build that circuit. Let me show you one other thing here. You're going to need to change the resistances. In order to do that, you can't click on the label. You have to click on the resistor. It'll put this little box here, and you can change those resistors to your heart's content. You are going to build a Wheatstone bridge. I've given you some data for R, RA, and RB. Then you'll mess around with that little bar that I just showed you to figure out to change the resistance of Rx until the bridge is balanced. You'll know it's balanced when the current in your ammeter reads 0. You get an ammeter by grabbing it over here. You can connect it where you want it to go. Okay, I'll let you play with that. Hopefully that'll be a little bit fun. You'll do 2 of those, and then you will move on to the second part on the calculations. Okay, so the PhET simulation, you'll do 2. You will take screenshots and you will submit those on Moodle. You can either take them with your phone or put them in a document. Okay, moving on here, trying to be quick. The second part of this is that we remember from a few labs ago that resistance depends on properties of the resistor. It depends on what is it made of. This is rho is our resistivity. That depends on the material. It depends on the length and the area, the cross-sectional area of a wire. So any wire has resistance. You can take a coil of wire of a certain length and a certain diameter. Remember, this is cross-sectional area. So area of a circle, pi r squared, or pi over 4 times the diameter of the wire squared. Okay, so that's cross-sectional area, length, and then this guy is the resistivity. Sorry, my pen doesn't like eyes very much. All right, so we combine that with what we already learned about the Wheatstone Bridge, where we can find this unknown Rx by knowing the other RBs and RAs. And what you would have done in lab is actually build this Wheatstone Bridge and gather information about the resistances. We would have done it, though, by looking at the lengths of a wire. Instead of the actual RB and RA, we would translate that to length. And you can see that if you read through your lab manual what that would kind of look like. But what that means is because R is directly proportional to L, you can rewrite this ratio in terms of L. cool. You can just say that the length of B over the length of A is the same as the ratio of RB over RA. Right? It's a ratio, it's directly proportional. This works if rho and A are the same. What does that mean? You have the same wire. It's made of the same material, say it's a copper wire, and it has a certain cross-sectional area. If they're the same, you can do this. This is equation 10 in your lab manual. So we're going to imagine that you did that and see what kind of data you got. Again, you go to this document and look, here's your data. You set up this experiment. You measured the lengths of the wire when the bridge was balanced. So you added a known R. You measured these lengths to represent the resistivities of A and B, and you balanced the bridge. Good for you. The unknown here is the spool. So your final step in this lab is to do some analysis. And I want you to read in your lab manual about how you're going to do this. Right? This is going to be down here in your analysis. You're going to calculate the resistance of each spool. What do I mean when I say a spool? A spool would have looked like this. So we have these different spools of wire. Notice that we have some that are copper. Ours has one this is copper nickel. Ours has one that's called nickel silver. We have some that are 10 meters and some that are 20 meters. So we have different resistivities. We have different lengths. And we have different cross-sectional areas. Some are skinny, some are thick. You're imagining that you are doing this for these different types of spools. So what you're going to do is going back here, you're going to find the Rx for each spool using the data that I've given you. And then you're going to see how that data works with the actual physical properties of the spool. This is part 2 to study the relationship between resistance and wire properties. So, for example, you'll have 2 spools. The example in your lab manual is you have spool 1 and spool 3. So you'll know R1 and R3 because you will have just calculated it with this equation with the lengths. And you know that the difference between those 2 spools is their length. So what you do is you say, okay, well, if they're only different by length, and length is proportional to R, then the ratio of the resistances, R3 to R1, should be equal to the ratio of their lengths. Right? So you plug in the numbers. You just calculated R3 and R1, plug in those numbers, you get some value here. All right, that's my funky number. It should be equal to the ratio of the lengths. You have the data for the lengths. I gave you that too. No, I lied. I will give you that. It's not in this version, but I'll give it to you. You'll have the data for the lengths and what everything is made of and all of that awesome stuff. So your final step here as we're wrapping up this video is to calculate ratios. You will do this for length, you'll do this for material or resistivity, and you will do this for area. Be careful, I don't give you all the answers. Think about this equation. How is R related to rho? How is R related to A? And you'll have to think about how to set up those ratios. Okay? Have questions? Let us know. Your last thing, don't forget you'll have a Moodle quiz as well. Have a good one.